Well, hello, good evening. This is the start of Chapter 13. Chapter 13 is entitled Coulomb's Law and the Electric Field, and we finally begin the whole series of the next 4 chapters dealing with electricity and magnetism, and electric circuits and motors and all the things dealing with electric fields and magnetic fields. So, and this is beginning page 423. Electrostatics, and this is really, this chapter here for chapter 13 is really comes under the title of electrostatics. Electrostatics, and what we mean, this is right on page 423. Electrostatics is a study of static charges at rest. So, in a static case, the charges are not moving. And what we do is we calculate, and basically in this chapter we will learn Coulomb's law and also how to calculate what's called the electric field, and we'll solve problems involving both electric charges and the corresponding forces, Coulomb forces we call it, and the electric field. But only with the charges at rest. When the charges start moving, that's what we call, well, it's not a static condition anymore, it's called a dynamic system. And so that we'll save for later on. But just to give you a preview of things to come, if you take a static electric field, if you take an electric charge and you move that electric charge, then the movement of that electric charge, when electric charge is moving at a certain velocity, it generates a magnetic field. So a magnetic field is really a result of a moving electric charge. So in a way, and we'll talk more about this later, in a way we say the electric field and the magnetic field, and we think of them as we can think of them as two separate individual forces, but in reality they're really two sides kind of the same force. And this is why physicists and electrical engineers call it the electromagnetic force. And so, but all of those details of how the magnetic force interacts with the electric force, we will deal with that in subsequent chapters. This chapter here is primarily just only dealing with electric charges in the static condition. So there's no magnetic fields for chapter 13. Actually, nor will there be in chapter 14. So, as you know, you've probably had this from chemistry, electric charges come in 2 varieties. We have plus charges and we have minus charges. Okay, and as far as we know, excuse me. Thank you. Bless you. As far as those are the only 2 varieties that charges come in: plus charge and minus charge. And as you know from chemistry, the proton is the subatomic particle that carries a plus charge. The electron is a subatomic particle that carries the minus charge. And your typical, as you learn from chemistry, your typical atomic structure is you have a atomic nucleus. So you have a neutron, which is neutral, and a proton. You may have, say you have 2 neutrons and 2 protons, actually, that are bound together in an atomic nucleus. That would be like the helium atom, with 2 protons and 4 what we call 4 nucleons, 4 particles. And then we have an electron orbiting. In fact, for helium, we have 2 electrons that orbit. Okay, so and the first thing you notice is that and you know this from chemistry, is neutral atoms like helium, say, will have +2 protons and 2 electrons. So, and we have the total charge, the net charge is 0. As we say, these cancel each other out, so the net charge of like a helium atom, a neutral helium atom, is 0. There is no net charge. And this, and now so we can take this and we can carry this analogy on to the world, and in fact the universe in general, and later on we'll talk about this in general. There tends to be a balance of charges. If you look over all of, if you look at a particular piece of material, in general, there's a balance of charges over that material. Equal number of plus charges, equal number of minus charges. Now you can offset that balance. You can charge something positively or charge something negatively, but if you bleed that charge off, generally nature, nature, by the way that the charges tend to recombine, and so in general, by the nature of things, we tend to have materials that have 0 charge balance. Okay, now, if you look on page 425, okay, there's the first part of the chapter I'm going to go through relatively quickly. Well, let me go back. On page 426, and we call that what I just spoke about, we actually is on top page 426. We call it the law of charge conservation, which is a net amount of electric charge in the universe is constant. And not only is net amount of electric charge constant, but it's balanced too. It tends to be very balanced. If you look at any one material, like we said, nature tends to always have a balance of positive charges and negative charges. Notice the law of charge conservation, the net amount of electric charge in the universe is constant. Can we create or annihilate electrons or protons? Well, we can't. Well, normally we can't. In the general scheme of things, we cannot destroy charges. Actually, if you look at what physicists are doing with these atom smashers, turns out you can smash a proton. Now, but we'll talk about that in just a minute. First, talk about the charge, the way charges stack up. For instance, we have, if we had an atom either has 1 electron or 2 electrons or 3 electrons, et cetera, et cetera, et cetera. So we only have and this is kind of the quantum of the quantized effect. We know that electrons only come as individual electrons. We don't find a half an electron floating around somewhere. So same thing with a proton. Protons only come in individual packets, just 1 proton. Now, here's the if what I just said is basically correct, but actually from particle physics, and if you get advanced physics, for instance, you will find out, and we'll talk about this later, that actually, can you subdivide a charge? Well, up until maybe 30 years ago, everybody said no. Or maybe 40 years ago, everybody said no, you can't subdivide charges. Or maybe even 30 years ago, you can't subdivide a proton. Well, we now know you can. Okay, so sorry about that. But now we know that actually a proton is made up of 3 individual quarks. Okay, and these quarks, each individual quarks have charges like +2/3. Okay, so turns out you can subdivide these charges even more. The electron you cannot subdivide, at least from what we know right now, the electron cannot be subdivided anymore. but a proton certainly can be subdivided into three individual, and they're called quarks. And there's different types of quarks. They come in different sizes and different charges. And so basically the individual, it appears that these subatomic particles can be divided down to the charge of like a 1/3 or 2/3. Because there are three individual quarks in one proton. But we're not going to talk about that anymore, basically. In general, unless you get to really, really, really high energies, and it takes enormous energies like you would have at an atom smasher, at one of these linear accelerators, unless you have really, really high energies like that to smash protons, you're not going to see the individual quarks. So, flipping back to page 425, electrons can move, and protons can move, and this movement is through a conductor. So a conductor is something that can carry, or shall we say transport. It's a transportation highway, if you call it that, of charges. A conductor, typically we think of a wire as a conductor, but there's many other types of conductors. But say like a copper conductor will allow the free flow of electrons going one way. And when we speak of electron flow going one way, we can also speak of plus flow going the other way. We'll talk about that later in next two chapters. But so a conductor is something that allows charges to move back and forth, and an insulator, excuse me, an insulator is something that will not do that. An insulator is something that charges cannot flow through. Okay, good example of this would be plastic or rubber. Glass is a very good insulator. So if you look at the copper wire, oftentimes they'll put a outer coating on the wire that's an insulator, and that's maybe plastic, some type of plastic. That's a wire. So if you grab a hold of that wire, the charge won't pass through the insulator, and you won't be shocked. Okay. So if we notice I have a new eraser here. Isn't that nice? My wife got it for me. Okay. This is on page, actually we're going to talk now about, look on page 428 and 429. We're going to talk about two types of charging. And there's what we call charging by conduction. Okay. There's charging by conduction, and then we're going to have what we call charging by induction. Okay. First, let's go over charging by conduction. If suppose I have, through some mechanism, I have a material over here that has a net positive charge. And I have a lot of net positive charges over here. I may also have negative charges here, but the positive charges far outweigh the negative charges. So overall, I have a net positive charge. Okay? And then I have a material over here that is electrically neutral. That is, the number of negative charge and number of positive charges are balanced. When we mean neutral, that's exactly what we mean. That the negative charges and the positive charges are equal, and there's a balance of charge. There is no net charge. Can there be individual charges on it? Absolutely. All material is made up of positive and negative charges, but there's a balance of the charges, and so there's no neutral net. There's a neutral net charge. Now, if I take a piece of wire and I connect it to here, and I take that piece of wire and I touch the wire to here, what will happen? This wire is a conductor, and the charges will actually flow along the wire such that we get an equal distribution of charges all throughout here. And so if I connect these two, some of the charges from here will migrate over to the charges here, and throughout the entire system, actually from here to here and even the conductor, will get a uniform distribution of charge. Okay, so this is what we mean charging by conduction. We have now charged this neutral. We have charged this neutral body by conduction. We attached a conductor from this material to this material. Okay. Notice when you do this, there has to be physical contact of something. Okay. In this case, these two bodies are in physical contact through the actual wire, through the conductor. Now, what can also happen is that sometimes could this same thing happen, but without the wire? Well, in special conditions it can, but what's happening is that the air itself is normally an insulator. That is, air won't air doesn't conduct electricity very well. However, we can have a certain situation where, for instance, we raise the voltage. Say this is neutral again. This is neutral. We raise this voltage. We haven't even talked about voltage yet. But basically, we raise the charge on here very, 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 very high. And what happens is we can actually, we'll talk about this next chapter, we can actually ionize the air to where there's so much of a voltage potential across here, we call it a spark. And what that spark is, spark through the air, the spark basically is a flow of charge actually through the air itself, through kind of a channel in the air. That's what a spark is. And if we do that, the charges will flow. And we have a conductor, but the conductor is the air itself that's been what we call ionized air. This happens all the time when, especially in the wintertime, if you walk across a carpet and you touch a doorknob, a piece of metal, the air ionizes because there's quite a lot of voltage potential, and you can see and feel the spark. Okay. Now, charging by induction, in charging by induction, what we have is we get a charge. Suppose, let me use an example. Suppose we have the same body, this plus charge over here. Okay. And what happens is we have this electrically neutral object, but we bring this neutral object close by. So we bring it in close proximity. It is not touching. It's not touching, but it's in close proximity. Okay. What can happen there is this charge induces a negative charge on this object simply because basically what happens is the positive charge is over here. Remember, this neutral object is made up of an equal number of plus charges and an equal number of negative charges. So it's not that there's zero charges. There's plus and minus charges in here, but they're uniformly distributed. But what happens is when this body comes close to it, the negative charges are attracted to the positive charges, and the positive charges get to be repelled. So what happens is we have just charged this object by induction. We've charged this side to one polarity and this side to the other polarity. And so, but notice there's no contact. Because if we then brought them in contact, what would happen? If we brought them in contact, assuming these are conductors, then the flow of charge would spread throughout uniformly. Okay? So, so we have two kinds of charging, therefore. We have charging by conduction. We have charging by conduction. And then we have charging by induction, where basically, now the other thing is suppose this were a really long, suppose this were a really long object, like that, the negative charges will all come here, the positive charges will be on the other side. So right in the general vicinity, you would generate a lot of negative charges. Okay, so basically, when you charge by conduction, you have a transfer of the same charge from one body to the other. When you charge by induction, there's no physical contact, and the charge that gets built up on the other body is the opposite charge of what you started with. Okay, so I hope that's clear. You can look at more in the if you read more, you can read more in the pages 426, 427, 428, and you really do need to read this. Okay. At this point, we're going to leave this, and we will talk more about this in the lab, actually. There's more details about that in the lab. But for now, we're going to leave this and go to Coulomb's law. And most of the chapter is going to be spent dealing on Coulomb's law. Coulomb was one of the early people that investigated this charges, and basically Coulomb's law. There's Coulomb. I think that's how you spell it. Okay, Coulomb's law, and we call it the Coulombic force, and I'll call it the Coulomb force between two charges is where K is a constant. K is a constant and is 9 times 10 to the 9th. Now we'll come up with the units in a second. Q is charge, and was charge number 1, and it can be either plus or minus. Q2 is the same thing, number 2, and again it can be either plus number or a minus number. R is in meters. R is in meters, and it's the distance between. So in other words, we have Q1 charge and Q2 charge. Two charges. This may be, let's say, plus 1, and the units here are coulombs. Coulombs. Plus 1 coulombs and plus 1 coulombs. Okay, so notice that this is a force, so this has units of newtons. It's a force, just like F equal ma, same kind of force. So this K must have units, so we have to have the overall is going to be newtons. Okay, but there's two charges, two coulombs here, coulomb squared, meter squared. Okay, so this, the K here must have units of Newton times meter squared divided by Coulomb squared. Because overall, when we multiply by charge 1 and charge 2, they cancel out the coulombs, and divide by r squared, that cancels out the meter squared, and we're left with newtons. Okay, so our K constant here will have units like this. In fact, this is 9 times 10 to the 9th Newton times meter squared per Coulomb squared. C, Coulomb being the unit for charge. Okay. Now, 1 Coulomb of charge is a very, very, very large number. And if you look in your book, the charge, for instance, the charge of 1 electron or 1 proton is very, 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 very small. If you look at this, the charge of one electron charge is, I'm looking at the front of the book, minus 1.6 times 10 to the minus 19 coulombs. Okay, so 1 electron, and a proton is the same number, just a plus charge, plus 1.6 times 10 to the minus 19 coulombs. We just use a capital C. So an electron and a proton themselves, they're in units of coulombs, but they're very, 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 very small. Okay, so if we say 1 coulomb, we're talking about a lot of electrons or a lot of protons. 10 to the 19th about. Okay. So, all right. So how does this work? Basically, if we have two charges, Q1, say, is plus 1, Q2 is plus 2, and they're separated by each other by R meters, then the force that they're going to feel, in this case, it's a repelling, two plus charges will repel each other. They will each feel a force on them that's the same. And it's given by this formula. Now, two plus charges repel each other. A plus opposite charges attract. That's the nature of charges. Okay, so we can calculate the size of the force. Now, very important point. Remember Newton's third law. For every force, there's an equal and opposite reaction force. If this force, the force, Coulomb force, tells us what the force is. Now, how do you know which one it applies to? Does it apply to this charge or does it apply to this charge? It applies to both. If it applies to one, the equal and opposite force has to be on the opposite direction, according to Newton's third law. For every force, there's an equal and opposite force. Okay? So this law tells us how much, so if you calculate this force for one charge, the other charge is going to feel the exact same force, but in the opposite direction. Now, remember, this is a force, so in this charge has, let's say this charge has a certain mass 1, this charge has a certain mass 2. The mass can become very, very, very different from the charge. Remember now, this is still F equal ma. We can still take Newton's second law, F equal ma, so we can still take this force, this Coulomb force, and say that's equal to mass times acceleration. In fact, we can do it in two ways. We can say, well, this force, this Coulombic force, will make charge 1 accelerate by a certain acceleration. And we can calculate that. We can say the acceleration that this charge will actually undergo is simply the Coulombic force divided by its mass. Similarly, the acceleration that the second charge will experience will be the exact same Coulombic force, but divided by mass 2. Now, if the masses are different, the accelerations will be very, very different. Okay, so nothing has changed with regards to Newton's laws. Newton's laws still apply. We can still say F equal ma, and then we can calculate physics, and we can do the physics on the charge, and it will accelerate, and it will cause the velocity to increase, and we can calculate distance. All the equations that we have in chapter 3 and 4 and 5 still apply. It's just that now we're introducing a brand new force, the Coulomb force. All right. Now, notice also something that I'm sure you've thought about already, and the early researchers thought about it a lot, and that's that. Notice that the gravitational law, Newton's gravity law, looks surprisingly similar. Now, notice how similar in form these laws are. They both